Hi, my name is Chris Murphy, and this is my natural language process investigation presentation for IST664. My topic is knowledge distillation, techniques to distill large models into smaller, more efficient versions. And specifically, I'll review a popular distilled natural language processing model named Distilbert. But first, it's important to build understanding of what knowledge distillation is, why it's important, and what are its benefits. The key takeaway for knowledge distillation is that we can take the knowledge learned by very large, complex, large language models and transfer that knowledge to smaller models. So we can think of knowledge distillation as creating a compressed version of that original large language model, and the capabilities can be transferred to a smaller, less complex, and more efficient model in a controlled manner. However, large language models have significant constraints serving as barriers to equitable growth of AI capabilities. First, industry experts acknowledge that the performance of large language models in many NLP tasks will continue to improve as more parameters are added to the model. As we increase layers and training data grows, parameters will increase. And we have not yet reached a plateau or an inflection point where capabilities no longer continue to improve with additional parameters. As of today, most large language models have many hundreds of billions of parameters, and this count is growing. This leads to models that require specialized and expensive compute resources like TPUs and GPUs that may be cost prohibitive. And as models grow and training data grows, it takes more time to build and train a model. Large models are not really portable to mobile edge devices, as there are constraints on storage size, processing speed, and power requirements that are not able to be met on battery-powered devices like smartphones. And of course, popular models like ChatGPT, Gemini, Claude have limited accessibility and higher cost. They're proprietary models. They often come with usage fees and restricted access, making them less attainable for individuals and perhaps smaller organizations. Also, there are some data privacy and security concerns as data has to be uploaded to the cloud for processing. So the constraints of accessibility, cost, and adaptability present some significant challenges in leveraging the full potential of proprietary large language models. Knowledge distillation enables broader growth in AI technology, and it processes a key critical role in compressing large language models, making them more efficient without significant loss in performance, leading to smaller models with reduced complexity, less computational requirements, less training time required, less costly operation, and importantly, increasing performance at inference time. They're simply faster. And this is achievable with open source models enabling access to a broader set of AI community and enabling equitable access. So distillation enables use of natural language processing models and applications where computational resources are limited, like mobile phones, smart devices, other edge computing devices, and increasing access. So now we'll take a look at how distillation works, what's needed for distillation, an overview of a basic example of a distillation process, and some additional information. So knowledge distillation requires four main components. The first component is a student-teacher architecture. And what this means is we have a teacher model and a student model. The teacher model is typically pre-trained on a large general-purpose corpus. So we're talking about models like GPT or Gemini or the BERT model, specifically for natural language processing. And the student network is typically chosen to be a small network with a streamlined architecture. And there are several options for student architecture design, but we'll focus on a very simple small model now. And as discussed on the last slide, open source models like these are provided by Llama or Mistral can be candidates for the student model. And as always during natural language processing or network training, data plays an essential role. A transfer set is usually a subset of the original data used to train the teacher model, and augmented data can be thought of as various permutations of this data to diversify the range of inputs. This process of creating augmented data can include things like paraphrasing, back translation, or masking, and it often avoids a requirement for massive data and compute resources for training the student. Next, distillation requires knowledge. And for this discussion, we'll focus on response-based knowledge, which is essentially the predictions of the output layer of the teacher model in response to the transfer data set. In industry lexicon, these probability predictions are often called soft targets, as they represent a probability distribution of the output layer rather than the classification of the data label, sometimes called the hard labels. I'll not dive into feature-based and relation-based knowledge in this presentation, but this essentially refers to leveraging additional feature information available from the inner or deeper layers of the network, and this can be thought of as feature maps or the relationships between feature maps. And finally, we have a distillation algorithm. And the algorithm essentially compares a difference between the output distributions created by both the teacher and the student in response to processing the transfer data set. The job of the distillation algorithm is to minimize the difference of the student predictions compared to the teacher's predictions for the same data. And the difference is called the distillation loss and is typically calculated as the Kullback-Leibler divergence, which is essentially the difference between the two probability distributions generated from each model. After this is calculated, the weights of the student neural network are essentially tuned to mimic the output of the teacher model as closely as possible. And this is really the secret sauce, is essentially that encodes knowledge learned by the teacher into the student. So next we'll do a basic review of one type of the distillation process, typically called offline distillation. And so we can review a basic workflow. First, we select both the teacher large language model and the design of the student model and the platform choice for the student model. The transfer data set is prepared. And if required, augmented data is created and used to train the student model. Data augmentation often has a positive effect in reducing distillation loss. The transfer data is processed by both the teacher and the student models, and the soft targets are compared. Distillation loss is calculated, and the student weights are updated to most closely approximate the teacher model output. In essence, the student learns to replicate the teacher's behavior based on the teacher's predictions or soft targets for a given input, not essentially directly from the data itself. Often this process is followed by some specialized fine-tuning of the model through additional training to ensure sensitivity or specificity to specific natural language processing tasks. In industry lexicon, sometimes this is called downstream tasks, so less generalized natural language processing and more focused on things, specific tasks for, as an example, speech recognition. Okay, now we'll transition over to specific distilled models for natural language processing. We'll review BERT, and then its distilled counterpart, DistillBERT. And then we'll briefly look at and discuss a few other examples. So first off, BERT. BERT is a pre-trained large language model for natural language processing tasks, and some of those use cases are things like questioning and answering, sentiment analysis, text classification, and named entity recognition. BERT stands for Bidirectional Encoder Representations from Transformers, which is essentially a fancy name for a descriptive name for its primary process of processing and encoding text from both the left to right and from right to left. So this bidirectional encoding enhances a contextual understanding of the language. BERT is trained on a massive data set of over 3+ billion words from sources like Wikipedia and Google's Books corpus. And these large informational data sets contributed to BERT's deep knowledge of the English language. However, BERT is very large and contains over 340 million parameters and required special tensor processing units and many days of dedicated training time to create and train. So while very useful, BERT is too large to use in environments like mobile or smart devices that have processing or power constraints. Therefore, it has been distilled. And that's where DistillBERT comes in. DistillBERT is one example where distillation increases access and enables growth of access to large language model capabilities. Distillation enables constrained organizations and teams to leverage the benefits of large language models in a more efficient and cost-effective manner. And in addition, the reduction of the model then enables usage of natural language processing capabilities in many different new applications. Key points for DistillBERT: it's much smaller than BERT, so from 340 million parameters down to 66 million parameters. It's 60% faster than BERT, which lends to implementing these capabilities in more real-time applications, and 50% fewer network layers than BERT. So it's smaller. It has a smaller number of parameters, but also smaller number of network layers. However, it still maintains 95% performance against BERT. So we are getting a huge benefit while trading off a very small percentage of performance to accuracy. And to that point, it's important to note that there are many industry benchmarks for natural language processing models. These benchmarks involve specific closed data sets that comprise the testing corpus and expected model metrics for things like speed, accuracy, and coverage of various natural language processing capabilities. These benchmarks were used to validate the performance metrics for DistillBERT that I'm displaying here on the screen. And these are just some examples for how distilled models can be used in mobile or edge applications. Mobile apps, perhaps question and answering type applications. IoT, perhaps processing sensor data in real time, so speed is important. Speaking to your smart devices requires voice recognition. Security solutions, perhaps analyzing environment description text from video feeds, which is also something that can be used in robotics. So these are some examples of what distilling large language models enables future growth of AI capabilities. Quickly, DistillBERT is not the only distilled model. There are many distilled models in existence, and these are just 5 very popular distilled models. TinyBERT and MobileBERT are even smaller versions of BERT for specific use cases. Distilled GPT is a distilled version of GPT-2, and so on. There are many more. And so I thought it would be important to mention the open source references, specifically Hugging Face, which is a platform that provides access to open source models. And I thought I'd take a few minutes to review where you can go to learn more and access specific distilled models. This is a screen capture from Hugging Face, and on the left-hand side, you can see I've highlighted natural language processing. You're able to select a natural language processing topic of interest, for example, text classification versus question answering versus translation, for example. And then in the upper main section of the page, you're able to search within that selection. In this case, I've searched for distill, and you can see the one of the first examples that's come up is DistillBERT. So I would encourage you to access Hugging Face and look for these distilled open source models that have been already pre-created and shared by other developers. Just a quick note on my sources and citations. I looked at a number of scientific papers, which are all accessible here. The links to the arxiv.org website are accompanied with each scientific paper. There are 12 of them, and then there are a number of web articles that also talk about distillation, should you want to dive in and learn more. I hope this was informative. Thank you very much.